So our divergence can be computed as follows. P tilde A, that is A is a vector field. P tilde is a scalar function. The divergence of a scalar function multiplying a vector field is the gradient of the scalar function inner product with the vector field plus P tilde multiplying the divergence of A. This is very easy. You consider by the definition of the divergence, you take the component of P tilde A and then taking derivative and using the multiplication law of partial derivative. Okay, you will obtain and then fix everything together, you will obtain this equality. This is an easy exercise to apply the definition of divergence and this multiplication law for partial derivative. Of course, I will not spend the time to explain this in more detail here. Okay, now the divergence of A is 0. We mentioned it before by Hadamard identity. Therefore, this is precisely we only have the inner product of the gradient with respect to A. But the gradient of P tilde is a function of x. P tilde is a function of x. So the gradient of P tilde is the component of the gradient of P tilde is the partial derivative of P tilde with respect to x. So this is the sum. This is the sum of P tilde with respect to xi, multiplying the ith component of A, that is ai, I from 1 to n. Okay, the inner product of two vectors is the sum of the corresponding multiplication of the components. So now we want to compute this partial derivative. We can apply the chain law. P tilde is the composition of P and phi. Y equal P. P tilde. Maybe I write here. P tilde x is P y x composition. So we can apply the chain law to compute the partial derivative of P tilde with respect to x. This will give us sum n I from 1 sum j from 1 p to yj to xi. This is the partial derivative of P tilde with respect to xi. Then copy the ai. Okay. Now we switch the order of these two summations. This expression first sum over j and then I. We switch the order. We write this by j from 1 I from 1 then the partial derivative of P with respect to yj has nothing to do with the summation index I. Therefore, we can move the partial derivative of P with respect to yj outside. Then what's this? What's this? We look at this. Look at this place. We know that this is, if j is not 1, it is 0. Otherwise, it is just the Jacobian determinant. Okay, so this is just j from 1 delta j1 Jacobian determinant, then p yj. Because of the delta j1 here, we only have the term corresponding to j equal to 1. Then this is p with respect to y1 then multiplying the Jacobian determinant. But the partial derivative of p with respect to y1 is just our f. Recall that our f is taken the p here. Our f, look at this. The partial derivative of p with respect to y1 is precisely our function f. Okay, so this is I will write it here. This is f phi x. It should be evaluated at the intermediate value, the corresponding y equal to phi x, then multiplying j phi x. So our result is that the divergence we want to compute equal very well to this function. This is precisely the function appears in our change of variable formula. Okay, now we can almost complete the proof. So by divergence theorem, the integral of fy dy, that is the integral of the partial derivative of p with respect to y1. And by divergence theorem, this is the integral over the boundary p nu 1 d sigma, the boundary surface integral. But the boundary of D has a parametrization. That is our map y. Okay, so using the parametrization of the boundary of D, we can convert this surface integral over the boundary of D by n-1 dimensional multiple integral over U. So so this is the U P nu 1, the norm of the normal vector given by the parametrization. Maybe I will write it more completely. P is a function of y. Nu 1 at the point. P is a function of y, but we are the variable in D is y, but the variable in U is small u. So to express the surface integral by integral n-1 integral over u, we need to express y in terms of u. So the integral should be pyu nu 1 u, then nu du. Nu is the normal vector on the boundary of u given by the parametrization y. Okay, now this term we already compute using Cauchy-Binet formula. Nu 1 multiplying the norm of u, we have just compute nu 1 multiplying the norm of u is the inner product of a and n theta. Okay, so we obtained that this is positive or negative pyu a n theta. Okay, du. And we write n theta. We notice that p theta is pc. Therefore, p theta. Pyu is y is phi x. Then this is p phi composition x. That is p theta x. Okay, so this integral can be written by p tilde xu, and then au an tilde, we can write it by a composition which the normal vector of n tilde multiplying the norm of n tilde, then du. But because the n tilde is the parametrization of the boundary of omega, and the n tilde, the norm of n tilde multiplying du is just the surface element on the boundary of omega. So this integral, this n-1 dimensional integral over u can be written by the surface integral of this function p tilde a inner product with nu tilde over the boundary of omega. Okay, if you cannot understand this, you just use the parametrization of the boundary of omega, x equal xu. You just use this parametrization of the boundary of omega. You can transfer the surface integral into a multiple integral over u. Then this is precisely the integral on the left hand side. So this is true. Okay, if you cannot understand in this way, you reverse the reasoning. Convert the surface integral into multiple integral. You will see that this is right. Okay. Now we obtain the surface integral over the boundary of omega, and the integral is a very good form. It is a scalar function multiplying a vector function. This is still a vector function or vector field. Vector field inner product with the outward normal vector, unit normal vector, fit into the form suitable for divergence theorem. Now we apply the divergence theorem again. This integral can be transformed into the integral over omega, over the domain. Then the integral is the divergence of p tilde a. Okay, here we apply the divergence theorem again, obtain this result. Now, this divergence we have computed in the last page. It is precisely our desired function f phi x, Jacobian determinant of phi at x. So this proves our result. Okay, so the change of variable formula for this special case. What special case? Our case require that the transformation phi to be C2. This is the first thing. We require the phi to be C2, and then we also phi to be C2, and also we require f to be C1. And also we require the domain of integration to be single. This is somewhat stronger assumption with respect to the classical form of the change of variable formula. But all this can be weakened. Smooth function can be approximated using continuous function can be approximated using a smooth function. So f is C1 can be weakened by f is just continuous. And also phi is C2 also can be approximated by C1 maps. And the omega single is a geometric assumption, but this can be can also be weakened can also be extended to the general situation. That is a Jordan domain. A Jordan domain can be filled with very many small balls. Fill in with very small balls. And in the small balls, because balls are single, therefore using our result, the change of variable formula is true on small balls. And then the summation of the integral over these small balls can be made as close as the integral over the domain omega or d, okay, as close as we want. Therefore, again, by an approximation procedure, we can eventually obtain the change of variable formula for general omega and the general phi, not necessarily say 2, and also general continuous function f. Okay, but due to the time limit, I will not present all these details. Okay, so the discussion of the change of a variable formula is ended here, and I remind you that our approach has an advantage, that is we can obtain this very important corollary very easily. Okay, just this several line we prove this difficult corollary, and this will lead to the n-dimensional Brouwer fixed point theorem, a very useful, powerful result, and a great theorem in 20th century mathematics. Okay.